Let's talk about attics. First, we'll need a house. Let's fancy it up a little, shall we? Great. During the warmer months of the year, the sun will heat up the house. As we know, heat rises, so it becomes concentrated within the attic of the house. In New England, it is common for the attic's temperature to reach around 45 degrees Celsius. Meanwhile, from the much cooler underground, we have municipal or well water lines entering the home. These pump in water at an average of 18 degrees Celsius. So, equipped with our knowledge of thermodynamics, the question becomes, can we use this temperature difference between the hot attic and the cold water to make useful work? Let's take a look inside the home to see where we might be able to do so. In many New England homes, water is pumped from underground into the home boiler, where it is heated and distributed throughout the home's heating system. In heating up this water, the boiling process requires energy, often in the form of oil or natural gas, both of which are carbon and energy intensive. But what if we could decrease this fuel consumption? Rather than pump water directly to the boiler, suppose we pump the water first to the attic, where the water would be preheated by the hot ambient temperature. Then, once the now preheated water enters the boiler, less energy is required to heat it to the desired temperature, hence saving energy. To test the feasibility of this system, let's do an experiment. The goal of the experiment was to determine the change in water temperature from one end of a heat exchanger to the other. This temperature difference, along with a few other system variables, could then be used to experimentally calculate the heat transfer coefficient of our system and help us theoretically determine the feasibility of implementing the system into a home. To help us maximize this change in temperature, let's first take a look at some equations regarding heat transfer. From the equation for free convection, we understand that heat transfer increases with surface area. From the equation for the heat transfer coefficient, we also understand that heat transfer increases with the velocity of air. Hence, to maximize the heat transfer from air to water, we would want to maximize the surface area and maximize the airflow of our heat exchanger. For our experiment, we used a relatively simple heat exchanger, a copper pipe. The original surface area of our pipe was about 0.15 meters squared. However, this value was unfortunately too small to yield any conclusive temperature change in the water from one side of the heat exchanger to the other. The heat exchanger we ultimately used was a 30-foot long pipe with over 1,000 metal fins. The surface area of this pipe was about 27 meters squared, nearly 200 times that of our original pipe. To maximize air velocity, we used box fans that generated an average wind speed of about 4 meters per second over the heat exchanger. For the experiment, hot water was pumped through a hose into one end of the heat exchanger. The water then flowed through the pipe and out into a bucket at the other end. The temperature of the water was recorded at both the intake and outtake of the heat exchanger using temperature sensors. Data was recorded and plotted on a Logger Pro. We also used a graduated cylinder to measure the mass flow rate of water through the heat exchanger. Ultimately, two tests were conducted, one with the fans on and one without. Without the fan, the water cooled by only 3 degrees Celsius, whereas with the fan, it cooled by 3.9 degrees Celsius. Hence, the fan test's greater difference in water temperature represents a greater amount of heat transfer, which was as expected. Using this result, the temperature difference between well water and the attic, and the average flow rate of water through household piping, we were then able to determine that our system would be able to warm the intake water by about 10 degrees Celsius, assuming there is a constant airflow of 4 meters per second circulating over it. If the design was to be actually implemented in homes, we would need to minimize the power consumption of the fans in order to maximize the energy savings created by the temperature difference of the water. To do so, we decided to make use of the temperature difference between the cold water and the attic's hot air to power a Stirling engine generator. The generated power would then be used to power the fans. Assuming an electrical generator efficiency of 20%, the Stirling engine with a maximum volume of 0.1 meters squared could generate enough energy from this temperature difference to power 7 box fans, more than enough to create constant airflow over the entire pipe. Unfortunately, Stirling engines of this size are not currently commercially available and are therefore very expensive, so actually installing one in a home is relatively impractical. Ultimately, there is still much research to be done into implementing this system into a home, including, but not limited to, material and installation costs, as well as total cost and energy savings. That being said, based on the size and cost of the necessary piping, and considering the system works efficiently for only a portion of the year, it is likely impractical to install such a system in most homes.